MU, and Jacob Wobbrock, my advisor. So this work is about improving text editing methods. Because we are now too much focusing on the text entry side. Some of the editing process is still uninvestigated. So imagine a scenario, the WIST results are just released, and you view the website, you found, oh, you got 5 papers accepted, and you are so excited, you want to tell your advisor this news instantly. So you write a fast text message, and you make so many errors because you type so fast, so excitingly. So what do you do to correct them? Let's see what we can do on current phones. The first way is use your finger to move the cursor to locate the error, and then delete it, and then retype the correction again. So there are 4 steps. The first one is place the cursor, and then delete it, and then type the correction, and put the cursor back if you want to continue typing, right? However, there are space to improve. The first thing is touch is imprecise. So it might take you a long time to place the cursor on the right spot. And then you might press the delete key multiple steps to remove a word or a phrase. And leaving the finger from the keyboard area breaks the typing flow. And all of this ruins your excitement of getting 5 papers. So how do we improve that? Let's first talk about the concept of text correction on mobile phones. Review the 4 steps. The only important one is type the correction because it tells you the mobile phone where to correct. The other steps are all navigations. So if we can skip those steps, we might improve the corrections procedure and make it faster. So let's think about it. Now we locate the error and we type the correction. But what if we type the correction first and then we use some way to apply it to the error place? So this becomes 2 steps. You type the correction, you apply it. And this concept is called type then correct. To support this concept, we implemented 3 interactions. And I will tell you one by one. The first one is called drag and drop. It is as simple as it hears. The first thing is to type the correction and then drag it to the error place. And while dragging, the text beneath your finger is highlighted in yellow. And just drop it to swap the word. Here's a demo.
Type the correction at the end, drag it to the error place, and drop it to substitute the error. You can also insert a correction by dropping on a space.
Pretty simple. The next one is drag and throw. It applies a similar strategy. However, it has 2 differences. The first one is you drag it from the suggestion list, which gives you more options. The second one is instead of drop exactly on the error, you throw it. So what is throw it? Let's see the demonstration here. Suppose you throw it and the landing point is not exactly on the error text. So here comes our algorithm, which will search for the neighboring text and finding the best candidate for the error. And it will change for you. Here's a demo. It's pretty fast.
First, type the correction. Drag the correction from the suggestion list and throw it to the error text. Then our deep learning algorithm will figure out how to apply the correction. It can also handle insertion corrections.
Okay, the last one is called magic key. So instead of directly interacting with the text, you can just press the correction button on the keyboard and it triggers the correction function. And then it will highlight the most probable error based on the algorithm output. and you can swipe on the button to navigate between different error candidates, and press it again to apply the error.
After typing the correction, tap the magic key to highlight a possible error. Tap the key again to apply the correction. Insert corrections as well. With magic key, you can just keep typing without leaving the keyboard area. This preserves the typing flow.
Okay, so the last two interactions both use an intelligent algorithm to detect the error place. And the algorithm is called the recurrent neural networks. And let me describe it in detail. Before we jump into the algorithm details, let's define the error type we usually make in the daily life. The first one is typos. And the second one is grammar errors. The last one is semantic substitutions, such as synonyms, or they have similar meanings, but you want to change the word or phrase. And let's define the input and output of the algorithm. The input will be the error text and also the user-typed correction text. So here in the example, it is thanks the reply, and the user typed the 4 to correct the phrase. And the output will be the error position, telling you where to correct the error. So in this example, it will tell you in the between thanks and the. And this is our model structure. For those who are not familiar with neural networks, it might look completely lost. So to make it easier, it is composed of two parts. The first one is encoder and decoder, and we utilize the attention layer for improving the performance. For more details about the attention mechanism, please refer to our paper. Let's talk about the encoder. So you can see multiple blue squares here. It is the identical recurrent neural networks. So I draw it multiple times just because we need to process the input every word each time. So there are multiple of them, but they are identical. They are reused each time. So that's why it's called recurrent. Every step, a word is fed into the encoders, such as thanks, and until the end of sentence mark is met. And together with the correction, the output will be fed into the attention layer and the next turn of the RNN. And here is the encoder. So next, the decoder has the similar structure of the encoder. First, it will receive the beginning of the sentence token here, and also the encoder output. And every step, it will output the correct text, and also the next will fed into the next round of the output. And I want to say a little about the output. So we all know that RNN is good at outputting sequential information, but how to make it output positional information? We did a little trick here. We only limited output to output 5 words, fix it to 5. So if it's not enough for 5, we use begin of sentence or end of sentence mark to fill the position. And we make the correction word in the middle. So by comparing the rest of the 4 words, which are always in the original text, we can know where to modify the error. For example, it's time to hitting the road. The user typed the correction hit, and the output will be time to hit the road. And by comparing it with the original text, you know it's to change hitting into hit. So for training, we use the Kernel Shared Task 2014, which is a correction task. And we also use Yelp and Amazon reviews. But the reviews good text, which means we had to inject errors into the text. We applied 4 strategies. The first one is typo simulation using a keyboard spatial model. And then dropping random words, word deformation, and using word2vec to apply semantic substitutions. Together, we have over 5 million phrases with errors for training. And for test dataset, we use Kernel and Wikipedia revision dataset over 3K phrases with errors. And here are the results. This gives us a little idea of how the model performs. But what we care about more is the accuracy of the real system performance. So let's see. So we did a user study to see the real performance. We had 2 tasks. The correction task to only evaluate the interaction, and the composition task to evaluate the interaction and also the model performance. For correction task, we had 30 phrases, and we ensured that our model can correct them correctly 100%. This is to isolate the effect of the model performance, and we only want to evaluate the performance of the interaction, such as throw or press a button. And phrases with error presented, the participants were told to correct them. For composition tasks, we asked the participant to type for 3 minutes, freely typing. But they are not allowed. They are told just to type it without make corrections. And after typing, they will make corrections in the end using different methods. And the way is to let them feel the techniques and provide realistic feedback. We run the neural network on a server with a single GTX card, and we use a Pixel 2 on 30 participants for the experiment. We modified the open source Android keyboard for this project. And here are the results. The x-axis are different error types, and the y-axis is the time in seconds. It shows how many seconds a correction make on average. Lower is better. So for all phrases, we can see the cursor-based is pretty slow, and also the drag and drop, and they are significantly slower than the other methods. To find more details, we see the typo and word change. The cursor-based, which are the method we are using now, is the slowest. However, in insertion, we notice that drag and drop is significantly slower than others. This is because for insertion errors, you have to drop the correction exactly on the space, and the space is pretty narrow. For the composition task, we did usability and TLX, which is task load score measurement. And for usability, the higher is better. For TLX, the lower is better. And we can see that participants preferred magic key in both evaluations. And we also log the accuracy while they are correcting the errors in composition task. And we can see the accuracy here. Drag and throw has over 87% of accuracy, and magic key has 97%. So it's pretty doable in the realistic settings. To conclude, we introduced a new concept, type then correct, for corrections. And we implemented 3 interactions to support the concept. We used RNN, the deep learning algorithm, to detect the errors. And by doing the user study, it shows us that by breaking from the traditional desktop paradigm, we can rethink the text entry and reach higher performance. We open source our data processing and neural network code on GitHub, and thank you for listening.
Questions for Ray?
Hi, Michel Baudouin-Lafont, Université Paris-Sud. Well, great work, although I've come to hate this autocorrection stuff when they go wrong. So what if the system doesn't do the right thing? How do you correct the wrong correction? And a related question is, oftentimes your system requires to retype the entire word, right? And sometimes the correction is just, adding one character or changing one character. So have you made a comparison cost of these two types of corrections?
Thank you. So the first question, how do I make rescue operations after if the correction is not right? I think that should be a future work for this study. One direction is making it absolutely more correct, and the other operation is, for the second operation, the magic key, you can navigate between different candidates, so that gives you more confidence and it can detect more errors. The second question is, sorry, could you repeat it again?
When you have a small
Oh yeah. So when you have a small error, I think for those kind of errors, the participant can just press the delete key, such as if you just realize the error and you just press the delete key. So this using scenario is more about further errors and which contains like more text to correct. Thank you.
Okay, one last quick question.
Sort of like a different version of Michelle's question. That is, so to summarize it, it's different degree of automated error correction techniques to a different degree. Like the drag and drop, essentially 0 degree of automation. The magic key is almost 100% automation, short of mind reading. Then it's kind of almost no-brainer that if you assume 100% model accuracy, then the more automation, the better it is. And your results essentially shows that. It's kind of almost no-brainer, but still good you did experiment, empirical studies on it. The rest really rests on the model's quality. And deep learning model quality is very, improving the quality it's years of work to do.
Yeah.
And also testing it is really hard.
Right.
We don't have good corpus to do that sort of thing. The existing methods of injecting errors to it, you essentially you're modeling your injection model, which is like a loop. So that's where the challenge is. I see.
Yeah, it's
But
definitely
certainly
a
it's
challenge.
progress,
Yeah. Of course, the contribution I think for this work is more on the concept. Like instead of just locating the error and type it again, you can just type the error and then locate it. Just like when we are in the conversation, if I make something mistake, I would just say I doesn't mean X, I mean Y. So that's the inspiration of this work. It's a new concept. And as for neural networks, it's really only a tool to implement those methods. And you can use more solid or robust algorithms. And I think there are pretty many of these algorithms to implement the interaction. Thank you.
Okay, thank you, Ray.